Let's begin working through some of these math with lenses problems that we have here. So we start with this one. A lens used as a magnifying glass. It's designed to have a magnification of +3, so that's going to be our M. When an object is placed exactly 10 centimeters from the lens, that's going to be our DO. And so we're obviously going to go ahead and we're going to be using our 1 over F equals 1 over DI plus 1 over DO equation here. The problem is we're looking for F here. We know DO, but we don't know DI. So before we go ahead and do that, we're going to have to also use our M equals negative di do, and that also equals hi ho here. However, we just care about this first part because those are the values we have. So we can say +3 is our magnification. Although we typically write the point O when we're writing it, we don't need that in the math part here. And that's going to be equal to negative di over do, which is 10. Go ahead and put that over 1 and cross multiply. And we end up getting that 30 equals negative di. So when we solve for di, we find that it's going to be negative 30 centimeters. So now that we have that, we can go ahead and sub that in to this equation here. So we can say 1 over F is equal to 1 over negative 30 plus 1 over 10. We find that 1 over F then is going to be equal to 0.067. It's rounded a little bit, but that's what the value ends up being. And then here we're going to go ahead and use that x to the minus first. So we're going to raise both sides to the negative first power. And that's going to allow us to solve for F. So this side just becomes F. And when we raise that 0.067 to the negative first power, we end up getting 15. So 15 centimeters is our focal length here. Second question asks what type of lens is used. We notice that this 15 here is positive, and whenever we have a positive focal length, that means it is a converging lens. All right, moving on to this next problem here. We have a microscope examining an amoeba on a slide here. So the amoeba has a length of 0.6 millimeters, but under the microscope it looks like it's 3 millimeters long and is a virtual image. So that tells us a few important things. Even though these are talking about lengths, this really is what we typically would call HO, the height of the object, and this is HI, the height of the image. Even though it's a length, height, same difference here. And the fact that it's a virtual image means that it's a positive HI. So what we can start with here, we ultimately want to find the focal length, but because we know HO and HI, and also we know the slide is placed 3 centimeters from the lens, that's going to be our DO, we can start with the equation M equals negative DI over DO, which equals HI over HO. We don't yet care about our M, although we will for part B, so we're just going to use this part of the equation. And so we get negative DI, which we don't know, over 3, and that's going to be equal to HI over HO. Now, we technically can get away without converting here because it's a ratio, so as long as DI and DO and HI and HO are in the same units, it doesn't matter that those units are different. You could convert millimeters here to centimeters, but I'm not going to bother because, like I said, as long as they're in the same units, it works. So HI is going to be 3.0 and HO is going to be 0.6. Notice I made this HI positive here because it's a virtual image, and so it's going to be upright and therefore have a positive image height. From here, I would go ahead and cross multiply, and so we can say that 9 is equal to 0.6 times negative DI, and we go ahead and solve for DI by dividing both sides by 0.6. We get that DI is equal to negative 15, and it's going to be units of centimeters here, and the reason for that is because DO is also in centimeters. From there, we can go ahead and set up our equation for focal length. So we can say 1 over F equals 1 over DI plus 1 over DO. So 1 over F is going to be equal to 1 over 3 plus 1 over negative 15. So we do our math here, and we find that 1 divided by our focal length here is going to be equal to 0.267. Once again, we're going to use that x to the minus 1 button to raise both sides to the negative first power, ultimately allowing us to solve for f, our focal length, and we end up getting a focal length here of 3.75, and it's going to be centimeters because that was the unit of both di and do. Let's move on to part B here. So for part B, we want to figure out what our magnification is. So I'm going to actually use this equation that we used before, but now I'm just going to take the m and say that's equal to hi over ho, because remember we can pick any two parts of that equation and set them equal to each other. And so when I go ahead and do that, I can say that our m here is going to be equal to 3, that was our image height, 3 millimeters, over our object height, which was 0.6 millimeters. And so I find that my magnification here is going to be 5. But remember, whenever we write it, we would say plus 5.0. So we're going to add that sign in front, add that decimal place at the end, and that's going to be our answer. Alright, so this last one's a little bit of a challenge here, but let's go ahead and attack this. So we're trying to figure out how far a candle is from a lens. We know the lens is a converging lens with a focal length of 30 centimeters, so we do have that piece of information. And then we actually know two other important things about this. We know that it's onto a screen, which tells us it is a real image, and we know that the image is twice as big. So that tells us that our magnification is going to have a value of 2, okay, because the image is twice as big. And the fact that it's real means it's inverted, so it's actually going to be negative 2.0. So we're going to have to use that magnification then in a second. So let's go ahead and start setting this up. So we have 1 over f equals 1 over di plus 1 over do. We do know our focal length here is 30. That was given. However, we don't know our image distance, and we also don't know our object distance. And that's where this magnification piece comes in. So we can say that magnification is negative di over do, or hi over ho. As per usual, we're just going to take two of these terms, so we'll take the first two here. And so what I can say is negative 2 equals negative di over do. Now you might think we don't know either one of these, this still isn't that helpful. However, what we can do is we can say negative 2 do equals negative di, so that means that di is just 2 do. And that actually allows us, with this equation and this equation, gives us enough information to be able to solve this, because I can substitute in 2 do for this di here. And so I end up getting 1 over 30 equals 1 over 2 do plus 1 over do. Here comes a slightly tricky part. We need to combine these fractions, so I'm going to end up multiplying this by 2 over 2 to give it a common denominator. So we can say 1 over 30 equals 1 over 2 do plus 2 over 2 do. Again, comes from multiplying top and bottom by 2. And then when I add those fractions, I get 1 over 30 is going to be equal to 3 over 2 do. Go ahead and cross multiply from here, and so I end up getting 90 equals 2 do. So do, which is all I was solving for, how far the candle is from the lens, is going to just be 45 centimeters. So it is a little bit of a tricky one, but if you read into it, there actually is a lot of information contained in here, even though it may not look like much to begin with.